computing information in a control flow graph. It computes information every edge in the control flow graph. And the way the worklist algorithm works is that it keeps a work list of all the nodes that are still left to be processed. And we start with all the nodes, or maybe just the entry node in the control flow graph. And while there's still nodes on the in the list, you take a node off the list, you process it. And when you process it, that may add more things to the list. And you just keep on doing that until there's nothing more to process. And the way you process a node is you basically run the flow function for that node. So this is kind of what you do for each time you process it, which is that you basically get all of the incoming information for that node, you apply the flow function, you get all the outgoing information, and then you update that into your map M. So M is the map from edges to data flow information. Does this make sense? Do people follow? So are there any questions on just the basic data flow analysis algorithm? This is a basic worklist data flow analysis algorithm. And the place we left off is termination. So can someone remind me why termination is important? Why can't we just stop in the middle?
Get the wrong answer.
Right, so we get the wrong answer. We actually, the way this algorithm works is that we start all the information with something that's not correct yet, and we kind of iterate and iterate and iterate until we reach a fixed point, or until nothing changes anymore. And at that point, we finally find an answer. If we don't go to completion, then we actually have incomplete information, which will actually lead us to incorrect answers. So does someone remember what we did with this algorithm to ensure termination for reaching definitions? Huh? So we added a union. So basically what we did is instead of just assigning this into here, we kind of unioned it in. And so actually the way you do it is you actually compute this new information on the outgoing edge. So you compute this new information, which is going to be whatever you got from your flow function, unioned in, which is this thing. That's the info out is what you got from your flow function, right? So info out is what the flow function is. And you union it in with whatever information you have stored in your map. So whatever your flow function is here, produces some output. You take this output and you see what you have stored in your current solution, you union those two, and then you check whether or not this thing is going to be, this new thing is going to be different. If it is, that's only when you assign it and you put the thing on the work list. So that's fine, but one of the things that you'll notice here is that this union is pretty nasty. Well, it's not totally nasty, but the thing is that this union is very specific to reaching definitions, right? In reaching definitions, we compute a set of particular, bindings of variables to the places where they were defined at each edge in the program point. But what if we want to compute something that's not a set? What if we want to compute something that's something different? Let's say a map, or at every edge in the control flow graph, we want to compute some information that may not be a set. It may be something totally different. So basically, this union is weird because it introduces into this generic algorithm the particular domain that we use in reaching definition. Now, let me just point out one thing, which is that actually I won't point it out. I won't show you the code, but there's actually one other place where the fact that we're dealing with sets comes in. You guys know where that is? It's not on this. It's not on this slide. It's on the previous slide. Hold on, let me find it. So where else? So this is the algorithm without the union in there. Where else in this algorithm is it pretty clear that we're using sets?
It's line 4.
Right, so we're initializing everything in the empty set. So because of this reason, and because we now are using union, we are encoding into our framework, into this algorithm, the fact that information at a point is a set. And that turns out that it's kind of a little bit more limiting than we'd like it to be. We'd like the information to be much more generic than that. And so what we're going to do is formalize this notion of what a generic piece of information that we can have at a particular program point using what are called lattices. So, do people know, have people heard of lattices before? Who has learned about lattices in logic? What?
You've mentioned it.
I mentioned it? What?
That's
No,
it.
not in this class. We haven't really seen it yet. Nobody. Cool. That's awesome. That's what we're going to learn them today.
Well, that is
If only I can get out of this thing. How do I exit? There we go. So, let's talk a little bit about what lattices are. So this is background material. It's not really, I mean, it's basically, this is not really compilers, this is math. So we're going to do a little bit of math. Okay? Are we all ready for this?
It's all right.
It's okay.
It's all right.
It's okay. It's just a little bit of math. And it's not too bad. So first off, some generic definitions. So this is actually, just from logic, it's relatively standard. So logic is very standard. So what we call a relation, so a relation over a set S is basically a set of pairs. Basically a set of pairs from S. Okay, so basically we're going to write kind of A, R, B to mean that, A, comma, B is in R. So basically, this is an example of how we write the relation. So what's an example of a relation? Less than, right, on numbers. 5 less than 10, right? That's an example of a relation over what? What's the set R? It will be integers, right? Okay. So we have all these definitions. So reflexive, basically, okay, that's what reflexive is. Transitive. So actually reflexive means that basically for any element, that element is related to itself. So for example, in the less than relation, is the less than relation reflexive? No, because 5 less than 5 does not hold. But what about less than or equal? That's reflexive because 5, for any element, x is less than or equal to x. So that's reflexive. Transitive is basically that if basically A is related to B and B is related to C, then A is related to C. Symmetric is that basically if A is related to B, then B is related to A. Antisymmetric, so this is actually the wrong definition. I'm actually not going to go to. Usually we talk about why it's wrong, but let's not worry about that. Antisymmetric is actually this, which is that basically if A are B and B are A, then A is equal to B. So basically, yeah, so that's just the definition. It's not that important to understand those details. But once we have these basic definitions, there's two things that we're worried about. Actually, so what's an equivalence class? An equivalence class is a relation that has 3 properties: reflexive, transitive, and symmetric. So reflexive, transitive, and symmetric. What's an example of that?
Equals.
Huh?
Equals.
Equals. Equals is reflexive. What is reflexive again? Oh, 5 equal to 5.
Yeah.
Transitive, if 5 is equal... Oh, wait. If 5 is equal to 5... No, this is... Okay, if A is equal to B and B is equal to C, then A is equal to C. And symmetric, I mean, you basically call it symmetric. Partial order. So it has to be reflexive, transitive, and anti-symmetric. So...
Less than.
Huh? So less than.
Equals.
Less than equals. Oh, okay, less than equals.
What was antisymmetric again?
Huh?
What was antisymmetric again?
I know. That's the let's talk about it in a second. So let's try less than. So less than is reflexive. Wait, is
No.
oh no, less than is not reflexive.
Less than
Okay,
equal.
That's already okay. So there we go. So we can remove it. So that's definitely not. Okay, less than or equal. It's reflexive. It's transitive. And what does antisymmetric mean? So basically, antisymmetric says that if A is less than or equal to B, and so this is basically and conjunction, right?
Right.
It's just a mathy funny way of saying and ampersand. and B less than or equal to A implies
A
A
equals
is
B.
equal to B.
Okay.
That's what anti-symmetric says. So, I mean, yeah. So it's really what it is that basically what is symmetric, right? Symmetric basically says that if A so
Greater than.
right, I mean, basically, it's so what anti-symmetric says is really that if A is less than B, then it's not the case that B is less than or equal to A. But actually, it's not entirely that. It's really more that if A is less than B and A is different from B. Okay, they're basically saying if A is less than B and they're different things, then you get this thing. Anyways, the logical details of that. You know, if you want to learn more about this, you can come to Alpha's house. Yes?
So what do you mean by A equals to B? Is this that like A and B are equivalent or?
No, they're equal.
So it's not equal.
Wait, so hold on. Wait. So there's a good question. So I really mean this here equals here is a special math equals. It's really equals. It's not like there's some equivalence relation that I have. It's just literally they're the same thing. So basically, A is related to B and B is related to A. The only way that can happen is that they're equal. They're the same thing. That's the only way you can get this kind of cycle. Okay. Oh boy, I hate it when that happens. Let me erase this. So, a partially ordered set is a set S with the relation. With not just a partial relation, it's a partial order. Oh, by the way, why is it called partial order?
It's not strong word.
It's not. Actually, it's not. No, it's not.
Partial.
It's not the word strong. Partial, what's the opposite of partial?
Full?
What? Total. Total ordering. So what would be a total order? So actually the numbers, the integer numbers.
It can be partial because you can have two things in there that are equivalent.
Right, exactly. So you can have, so basically, it's partial. Actually, let's talk about the total first. So what total order is when you have two elements, any two integers, you'll either have that A is less than or equal to B, or B is less than or equal to A is less than or equal to B, or B is less than or equal to A. Right? So basically, if I pick any two integers, I know that either this will hold, or that will hold, or both. But at least one of the two will hold. In a partial order, you may actually have two elements in this set S that for which there's that neither A or B holds, nor B or A holds. Okay? Because there's nothing in this thing that forces that. Right? I can have two things that are what are called incomparable. Does that make sense? So two things that I cannot compare. Now, what's an example of partially ordered sets? So this is a great example. What's this example?
Subset.
Yeah, so 2 to the power s. That's a very funny notation. Also called the power set notation. So what does this expression mean? Also sometimes written like that. So let's say S is a set. What does this represent? Right, so it's a set that basically contains inside of it every subset of S, which includes S itself, right? Because it's S and all of its subsets. So basically it includes any X that is a subset of S. So basically, for example, what would be, so if we have, for example, let's say S is AB, then what would be the power set of S? So we'd have AB and then what?
A,
B, null set.
And then the empty set, right? because the empty set is also a subset. So, and the ordering, so there's multiple ordering that you can do on this. So one ordering is the subset relation. Right, so that's the subset relation is a partial order. It's reflexive, it's transitive, and it's antisymmetric. And you notice how it's a partial order because these two elements are not comparable, right? I take these two elements, and neither one is a subset of the other. Okay? Okay, does it make sense so far? I mean, there's other examples here. So, so a totally ordered set is also a partially ordered set. So, so these things are also, if it's totally ordered, it turns out it's also partially ordered. But the point, yeah. And you can also, it turns out that there's many, if you look at the theorem math, there's a lot of these different kinds of partially ordered sets. For our purposes, we're not going to use many different kinds, but it's important to kind of understand the concept. Okay, so now we're almost there, The pain is almost gone. It's okay. Don't worry. We're getting there. Okay, now we have these things called loves and gloves. Okay, we gotta grind through this. Okay. So we have a partial order set S and the relation less. So I'm just gonna say less than or equal, but it's not less than or equal. It's just a relation. I'm calling it that. But okay, so a least upper bound. Oh my gosh, this is overwhelming. Okay, so what is a least upper bound? A least upper bound of two elements. So it's a least upper bound of A and B. Is going to be an upper bound on A and B. It has to be an upper bound on A and B, and it has to be the smallest upper bound on A and B. Right, does that make sense? So that's what least upper bound means. It's got to be an upper bound, and it's got to be least, right? It's like least upper bound. Okay, what does it mean to be an upper bound on A and B? So I have A, I have B. What does it mean to be an upper bound?
They're both less than it?
Right. Wait. I think that's right. I just need to kind of wait. So
or equal.
It's an upper bound, so I have two things
that are not greater.
Right, so basically the upper bound has to be larger than both of these things, right? So I have...
or equal.
Oh yeah, or equal. Sorry. Whenever I say larger, it really means larger by the definition of this relation. So it's this relation has inside, so because this relation is already reflexive, it has inside of it encoded the notion of or equal. So, wait. So we have A, and we have B. So an upper bound is something, a C, that is greater than, according to the relation. So there's a relation here called, here I'm calling it this, but it's really an R here, any relation R. So it's really saying that, basically I have CRA and CRB.
No.
Right?
No, AR.
Oh, sorry. No, sorry. Totally wrong. It's actually ARC, right? So ARC means that A is less than C. And BRC. Okay? So this is ARC, BRC. Cool. So C is an upper bound, but on top of that, C has to be the least upper bound. How do you say it's the least upper bound? How do you say that anything is the least?
For anything that satisfies, for any D such that ARD and BRD is true.
You're reading it off there.
Oh, I'm looking at it. There's nothing.
Nothing in between it.
There's nothing that can be on the right side of A or B in this set, such that C cannot be on the left side.
Right. No, I was kidding. Reading it. Because actually, sometimes coming up with that thing is exactly what that is. But the intuition is that basically you're saying this is an upper bound, and basically what you want to say is any upper bound, no matter what upper bound I pick, because there could be multiple upper bounds. For sure, actually, there could be multiple upper bounds. Right? It's like, in fact, in the set thing, what's the upper? There could be many different upper bounds.
Any D.
Any other upper bound D, I'll have that D is going to be, C is going to be smaller than that. Right? So any other upper bound D, C is going to be small. And that's exactly what this thing says. For any other upper bound, so basically upper bound means that it basically satisfies these two things. So for any other D that's greater than A and B, C is going to be less than that. So that's least upper bound. And then there's a symmetric definition. Does that make sense, actually? These are right, yeah.
I think where you have R on the diagram, I think it's literally greater than, not
Well,
R.
Well, yeah. So I'm calling this thing. I'm just using a naming. Maybe this is not the best naming, but I'm using this as the name of my relation.
Yeah,
It's just the name, but so you're right. I mean, this should be this.
I'm saying that whatever the relation is,
Right.
that sign there should always be greater than.
No. It's just whatever the relation is here. So if I put an R in here, then this should be R, and this should be R. For example, if I'm using, okay, let me give you an example. So if I'm using sets, right, then this should be the subset relation, right? And if this is number, then this is going to be a less than or equal relationship. So it's really the R, whatever the R is in the relation that we're using. Yeah.
So let's say A is less than B. So would B be the least upper bound of A and B?
Hold on. So if A is less than B, so we're going to a lot of times use this notion of less. We're going to say less than when what we really mean is that this is, we have A, R, B. In other words, A is less than B using the relation R. So if A is less than B, then you are asking...
Is B the least upper bound of A and B?
Oh, for sure.
Okay.
So so in this case, if you have this, then it degenerates, then B is the least upper bound. In fact, you can show that mathematically. You can actually show that B satisfies exactly this property.
So B equals to C in that case.
Oh, no. I mean, were you asking as a separate example or in that example? I mean, sure. In that case, yeah. So in that case, if A is, then C is actually A. Right.
B. We don't know. It can't be. It could be A or B.
Oh, sorry. Yeah, well, it depends on how you put it up. So if B is the bigger one, then C is equal to B.
Right.
So C is the maximum.
Right. Exactly. Well,
Maybe.
No. But careful because max.
It can be.
So max is so this is a generalization of max. Okay, because max, it's like, for example, in integers, you get two integers, give me the maxes of two integers.
For something like subset, whatever.
But in this case, actually, so whenever you give the max of two integers, you will always get back one of those two integers. But for example, actually, let me give you, this is a great example. If I have this, right? So the least upper bound of these two things is a different thing, right? The third set that is bigger than both. So that's why it's a generalization. Max is really only, it's kind of a concept that works for what's it called? For total orders. This is kind of a generalization in a setting where you actually have this partial order. Okay, there's a symmetric thing called the greatest lower bound. Should I go through it, or you guys see the symmetry, right?
Yeah.
Yeah. Okay. So it's a similar thing, but. So if you have A and B, then the greatest lower bound will give you something that's below both. And it'll give you the greatest such thing that's below both. Right? Because there can be many, many things that are below. It'll give you the greatest such thing. Okay? So one of the things is that in general, in a partial order, loves and gloves don't always exist. Okay, so you can actually create relations in which you actually don't have, there are two elements that don't have a particular, a least upper bound. So an example would be something where,
A and B without.
They just don't have bigger elements. There's nothing that it's like you have maybe something like this, where there's something here, there's something below them, but there's nothing above. And so if I ask what's the greatest lower bound is this one of these shown. What's the least upper bound? There is no upper bound. Like there is no, right? So in some sense, these two elements are kind of local maxima, right? They're kind of in this point where there's nothing that kind of supersedes both of them. So for a variety of reasons, that's kind of annoying when these things don't exist, when these loves and gloves don't exist. So this is where lattices come in. So a lattice is really just a partially ordered set where loves and gloves always exist. Okay, if you just give in two elements, you always have a glove and love. So basically, lattice is basically it's a partially ordered set S, and we usually write it like this: the relation. Okay, so it's a square less than or equal. There's a bottom element and a top element, which the top element is greater than everything else, and the bottom element is less than everything else. And this in part, well, yeah, I mean, so yeah, so you have
which of those are the
element
top?
and what?
Which one's considered the top and bottom in that?
The T?
Is it T top or is?
Yeah, that's top and that's bottom.
Yep.
That's T for top,
Okay.
and that's B for bottom. No, it's not B for bottom. I don't know why they do it this way. That's just yeah. So
It's visual.
I was just curious.
Yeah. So this is top. That's bottom. So for basically the property of bottom is that for any element of S, bottom is less than or equal to that element. For any element of S, A is less than or equal to the top. Every two elements in S have a love and a glove, and the love and glove operators are basically these things. So the least upper bound is called a join, and it's this thing here, and that's the greatest lower bound is a mean.
What's the difference of the least upper bound?
The least upper. So top is an upper bound on everything, but it may not be the least upper bound.
Okay, so there's one least upper bound and
No. So there's only one T that's bigger than everything else. We'll see in a second an example. There's one T, there's one top, so the way you can think about it is like this. There's one top and one bottom. And in here, there's a whole, there's a lot of things in here. And in here, you can have two elements, and you can have something like this. Right? The ordering basically is that top is greater than these two elements, but top is not the least upper bound. There's another upper bound that's smaller than top. Okay? So top is an upper bound on everything, but it may not be the least upper bound. So this is so hold on. This is the least upper bound, and it's called the join. Okay, I don't know how you get it to remember this.
Yeah, it's ridiculous.
I don't know how you get it to remember this, but I'm going to try to tell you how I remember it. So this is called the join because it's like a J.
Yeah.
And this is called a mean because it's kind of like an M.
Brilliant.
Okay? That's one way to remember it. Also, there's also, so the join, so the join, the other thing to remember is that the join, which we call this a join, it's actually the least upper bound. So in fact, the join actually goes up, right? If you have two things like this and you join these two things, it goes upwards.
Mm.
That looks like a smiley face. That was not intentional. But I mean, the point is, if you take two things and you join them, it somehow
It's a
goes
unicorn.
upwards. And whatever you need to use to remember that, this thing goes upwards and this thing goes downwards. Okay.
U for upper.
What?
U for upper.
U for upwards, and yeah. So that's one way to do it. Sure. Okay, let's see some examples of lattices. So this is a power set lattice. So this is by the way, this is a power set lattice with three elements, A, B, C. So the nodes here, basically the elements here of the set are what? Each element here is a subset of S, right? Where S is, sorry. I'll just write it down. right? Basically, each element of S is a subset of ABC. So in other words, S is a set of all subsets of ABC. Does that make sense? Or you guys confused it? You gotta like,
Yeah.
so it requires your brain needs to be a little bit like, it's rejiggled. Does that make, so every element here, this is a subset of S. This is a subset of, no, sorry, oh. This is a subset of ABC. This is a subset of ABC. That's a subset of ABC. Each one of these things is a subset of ABC. All of these things together are the set S over which our lattice is defined. And all of these elements together, this set S, mathematically is the power set of ABC. Right? Because what's a power set of ABC? It's a set of all subsets of ABC. Anybody have a question on this?
This is a cube.
Yeah, it's not a lattice. Cheating.
Whoa. What do you mean by a cube? It looks like a cube. It looks like a 3D cube. But what do you mean by a cube? I mean mathematically or?
No.
Oh, it's a cube.
It looks like
it looks like a cube. Absolutely. But the question is, which is the, actually, the question is, which is the corner that's popping out at you?
ABC.
No,
So we got
actually,
8 vertices.
B is on the bottom.
See, it's either this thing is the one that's popping out in 3D,
Oh, sure.
or it's this one, right?
No.
You guys see both things? You can
No. B is on the bottom. It's a tesseract.
Okay, but this is making our brain hurt even more now. It's like we're supposed. Okay, so but does everybody understand that what's going on here, which is that this lattice, the elements of the set S, every element of the set S is a subset of ABC, and the elements of the set S are this one, this one, this one, this one, this one, all these ones here, right? So now, what's the relation? Actually, wait, hold on. What's top and bottom?
Top is ABC. Bottom is
Empty.
top is ABC.
Top is ABC?
If your relation is subset, yes.
So is it? What? Absolutely. So this was a trick question. Actually, there's two ways. There's
your
two ways to
relation is
order
subset,
this. Actually, there are two ways to do this, in the sense that there's actually two different lattices you can define here. One is where this is bottom and that's top, and the other one is where it's inverted, and that will affect all of these operators. In general, the way we're going to draw these is that we're going to generally draw the top at the top and the bottom at the bottom, so we'll just do it this way. So let's just assume that it's this way. But if you want to do it the other way around, you can literally draw this thing upside down and then have the top be at the top and with the full set. And that's a totally valid lattice, where the top is the full set. But yeah, okay. If after, we'll get to that. Actually, we'll get to that in a second. So, what are these operators? So what is the relation operator in our lattice, in this case?
Not subset.
What?
Not subset.
Okay, so I'll give you,
Or superset.
let's see, yeah, so it's going to be either this or it's going to be that. It's going to be one of these two.
The right.
Yeah.
The second.
So it's the right one, right? Because if you look at this, should be smaller than that, right? So we want A comma C to be, right? So we want A comma C, right? A comma C, we want A comma C to be less than A. So if we plug this symbol in, we want A comma C to be less, actually the way you can think about it is this way. You can actually just draw it out literally. You can say, look, this is what we want, right? According to our lattice, which is the square thing, this should be lower in order than that. And so if you plug in this thing in here, that's totally bogus, right? This is not a subset. If you plug in that one, whoa, that works. Right? Do people see that? Yeah.
Why do we have no arrows in the graph?
Oh, so that's true. So in general, you should have arrows. What we're doing is what we're actually doing is the assumption we're doing is that the order in which these things work is that there's the we're never going to draw arrows sideways. We're also going to have arrows that have some y differential. And whenever we have a y differential, the one at the top is going to be the one that's greater, and the one at the bottom is going to be the one that's less than. So whenever we have all of this stuff, the implicit assumption is that this is less than that. So we have A comma C less than or equal to C. That's an A. Right? And by the way, we also have A is less than top. Right? That's also about, this is also a valid thing, right? We also have this. And we also have A comma C is less than top. We don't draw that explicitly because we only draw the kind of the unit relations because we know it's transitive. So because of transitivity, this will be greater than this. So this is just a way to draw and represent the relation. Does that make sense? Okay, so so what did we say? It's this one, right? It's greater or equal. What about this? So what is, so if we take the join, remember this is a join, the J, join. So we do the join of A and B, and you helped us run because that's a U, so it's up, going up. So A and B, well, this should give us top, right?
Yeah.
And so basically, what should this, and top is the empty set. So when we do this, what should this operator be? Should be union?
Intersection.
No. Intersection. So in fact, that's exactly right. This is intersection. So you can do this example on all of these things. If you take these two, you take the intersection of them, you get B, and this is the element right there. If you take these two elements, you do an intersection, what do you get? A. Right there.
Oh, okay.
Cool. And what's this one?
Union.
So, if we flipped everything around and we kind of had the full set up here and the empty set down here, what would the difference be? All these would be flipped.
Yeah.
This would be less subset, this would be union, and this would be intersection. Okay? Cool. Okay, let's take a look at a totally different example. So this is where you can kind of see the power of lattices. So basically we're going to do Boolean expressions over one variable, just one variable. So there are 4 possible expressions, Boolean expressions, if you have one variable and negation. Okay? So there's true, false, A, and not A. And I've ordered them. This is what the lattice is going to look like. So now, if you look at this, where's top and bottom? So we said that the way we order things, we'd like top to be here and bottom to be here. And notice how this T is completely different from that T. Very, very different.
It's bold.
Very bold. It's a very bold T. Why is it such a bold T?
It's
It's top. This one's top, and this one is true. Right? This is just a Boolean true. That's the Boolean false, Boolean true. This is A not A. So what's the relation now?
Union is, or
Ugh. Oh boy. Okay, let's take it one step at a time. So
not false.
So do we certainly? So when you're looking at these things, one of the way to do it is by concrete example. So certainly, what is the most obvious fact that we know about these things? We obviously always know that bottom is less than or equal to top, right? Because bottom is the smallest element, top is the biggest thing. So what would be this? So basically what we want is we want false. This is false and that's true. So we want a logical connective here that will kind of, when we put false there and true there, it'll hold. What? Okay. Or I know I heard. Okay.
Or would
So,
be the
or could, okay, so you're saying maybe it's
That'd be the
or.
join.
Hold on. So,
That's not anti-symmetric.
yeah, I mean, or, hold on a second. Where is or going to... Actually, can you just use or?
No, it's not anti-symmetric.
It's not anti-symmetric.
False or true is equivalent to true or false.
Wait, well, anti-symmetric is basically that A are B and B are A.
Implies B is equal to
That
A.
A is equal to B. So if I have, oh, actually that's totally true. Good catch.
Then we get true equals false. And we,
That doesn't. I mean, if you have A or B and B or A, that does not in any way help you equal to A.
although that would make branch prediction easy.
Yeah. But yes, that's right. So actually, it's not anti-symmetric. Okay, so that doesn't quite work. So we want something that is anti-symmetric. So what other connective could work here? What other connective do we have where if you give it false? In fact, so hold on. Let me just put one. Wait. What is this thing? This like that, right?
Mm-hmm.
We also know that A should be less than or equal to true, and not A should also be less than or equal to true. And we also want that false is like this, false is like this,
Can we arbitrarily...
and false is, oh, by the way, notice what's going on here, right? So I want false, I want this to hold like this to hold like that, and this to hold like that, right? These are the three things. So what logical connective holds as soon as they put a false on the left-hand side? Implication, right? Because I want false to basically, false goes there, it goes there, it goes there. So implication has exactly this property that if you do implies, basically this will actually work for these things. Now let's see, does it work for all of them?
False implies anything.
So this is our current proposal. So first of all, it actually is anti-symmetric because if A implies B and B implies A, then A is equal to B. So that's good. And does it work here? So false implies A, false implies not A.
False implies anything.
Right, it implies all things. Then A implies true, not A implies true. So it seems that it's actually working out.
Mm-hmm.
Are you guys confused? No, it's not. It's a simplification. So what about these things?
Or.
This is or. Is that or?
Yeah.
And. Right. So if you take these two things, you want to find the join. You basically or them. You want to find the meet. You and them. Okay. So it turns out that you can. This is for two variables. You can actually build something like this for. So that's for one variable. You can build these things for any number of variables. So you can actually build these huge lattices of expressions, and the ordering is going to be exactly the same. It'll be ordered by implication. You'll have false here, true there, and whenever you want to join two things, you basically you or them, and whenever you want to meet them, you do an and. Yeah.
A implies true, not A cannot imply true.
No, anything implies true.
No, and then
It doesn't matter. I mean, no. I mean, it's not. If I put something, if I have implies true, it doesn't matter what I put, right? Because I mean, right? I mean, the way implies works is if the right hand side of the implies is true, the left hand side does not matter. right? I mean, it doesn't matter.
The same way false implies anything.
Right, in the same way that false implies anything. Right? I mean, that's just the way implies works. It's true. Yeah, true. It doesn't matter. It just really doesn't matter when you put it. So, and actually, you can build these very complex, logical expressions and order them in this way. Okay. So, okay. Good news. That was the recap material. How painful was it? This is like those when you go to the hospital and they ask you, like, on a scale from 1 to 10, how much pain are you feeling right now? No, don't answer that.
11.
11?
You ever told them 2?
What?
If you ever tell them 2, they get scared.
What?
Give them a small number, they get scared. Say like 1 or 2, they get really...
Oh, really? If you tell them I feel no pain. Yeah, I'd be scared too if you told me, like, you gotta be, if you're feeling absolutely no pain, it means that maybe you're just asleep. But this could give you it should give you a little bit of like, oh, wait a minute, what happened, right?
Maybe it's after they give you the morphine.
Right.
Yeah.
So, so now, okay, what are we going to do now? So we're going to go back to, we're going to keep this. So we're done with this part. And what we're going to do now is go back to, okay, we're done with this. And so now we're going to go back, okay, so that was the end of the digression. And now, oh, wait, oh, come on. So now we're going to go back to our data flow analysis, and we're going to formalize it using lattices. And we'll see that actually there's some really, really cool stuff that comes up when you do this. So this is our worklist algorithm. If we do it using lattices, how are we going to do this? What were the 2 things we were really annoyed about? It was this empty set and this thing, right?
You want the ME defined as the bottom, and then instead of union, you want to use the join.
Okay. Now, is everybody happy with that? Okay. So, let me be a little bit contrarian. So let's say that I say, you know what? I don't like bottom. I like top. I like to start with top. So I'd like to do this.